Hello, in this video we're going to derive the energy eigenstates and eigenvalues of the harmonic oscillator using ladder operators. Now what happens if we act from the left with the state A dagger? We get this, but we can move the A dagger through the H using the commutator, because we can rewrite A dagger H as follows. H A dagger plus the commutator of A dagger H, because if you multiply this out, you get the A dagger H back minus the H A dagger, which comes here, and so we get the original form. But A dagger commutator with H we've just worked out, and it's this. We worked out H A dagger on the previous board and found H bar omega A dagger, so A dagger commutator H is minus that. So we can add this term over to the other side, because it's just an A dagger multiplying a ket n, and this gives us the result. Okay, so this is our result that's worth all the fuss. Let's take a look at it. What it's telling us is that we define n to be an eigenstate of the Hamiltonian with energy En, and so this tells us that the object in parentheses, because it's the same on both sides, must also be an eigenstate of the Hamiltonian, but this one has the energy En plus h bar omega. And so what this is telling us is that acting A dagger on the state n gives us something proportional to the state n plus 1. Okay, it's just increased the energy of the system, and you can keep doing this repeatedly, and you'll find that acting A dagger multiple times raises your energy, and each time it raises it by a fixed amount, h bar omega. So just as we saw in the differential equation case, there's an infinite ladder of states evenly spaced in energy. So we can state the following. A dagger acted m times on n, on the state n is a state proportional to n plus m. We'll find this the normalization shortly. And similarly, actually, if you make the same reasoning with A instead of A dagger, you find that that acts as a lowering operator. It lowers the energy each time. It gives you back another, acting on n, it gives another eigenstate with an energy which is lowered by h bar omega. So we're getting there with our solution. We know that there's an infinite ladder of states separated by energies h bar omega, but we need to work out what those energies actually are. So first of all, we need to look for the ground state of the system, that is the state with the lowest energy. So even though there's an infinite number of rungs of our ladder, there is a bottom rung. And let's find that now. Let's prove that's true and then find it. So first, the proof. So first of all, we know that for any vector whatsoever, and by extension any state, so any state in here, the norm square of that must be greater than or equal to 0, and it's equal to 0 if and only if the state itself is just the number 0. So that's true for the state A acting on n, but we can rewrite this as follows, because the norm squared of a ket, any ket, is just the bra acting on the ket, the bracket. So it's this. But we know that this is related to our Hamiltonian by the following expression. So it's Hamiltonian over h bar omega minus a half times the identity operator. But the Hamiltonian acting on an eigenstate n is just En. And so what we see and the identity operator acting on any state, including n, is just 1. And so we see that this quantity must be greater than or equal to 0. That is, En is greater than or equal to h bar omega over 2. So we haven't proven that this is the ground state energy yet, but what we have proven is that there's a bottom rung of the ladder, because there's a lowest possible energy. The energies can't go below this, and that means that there must be a bottom rung. So then there must exist a state, A acting on n, which gives us literally the value 0. Okay, so the existence of a bottom of the rung of the ladder means that if we act the annihilation operator, the lowering operator, on that state, this is a particular n now. We'll call this state n equals 0. So this is a ket 0. It's not the number 0. It's just a ket. It's a state in the Hilbert space labelled by the number 0, because it's going to be the ground state of the system. And by definition, in fact, this defines this state 0, acting the lowering operator on that state gives literally the number 0. So this isn't just a label, this is the number 0, whereas this one is n equals 0. We could also call this, if it's less confusing, we could go back to calling it phi, and then it would be phi 0, if that's a bit easier, but it's just the state 0. Okay, so there must be a state which obeys this property, and that we can use this to find the ground state wave function of the system. So starting from the defining equation of our ground state, 0, label 0, we can rewrite our, we can write things into the position basis by expanding our operator A. So first, written out in terms of position and momentum operators, we have this. Let's write things into the position basis. So the position operator is just x. The momentum operator is P is minus I h bar d by dx, which I've substituted in here. D by dx can be a total derivative because x is the only variable in the problem. And the ground state 0 projected into the x basis, let's write it phi 0 of x. We can't really write it just 0 of x, it doesn't really work. So another strength of the ket formalism is that we can give arbitrary labels like that, but when it comes to wave functions, we would use something like phi. Okay, well this is a simple differential equation to solve, and the result, it looks like this. So a Gaussian. This is the ground state wave function. And to find the ground state itself, the energy eigenvalue, we just substitute this back in to our time-independent Schrödinger equation. And we find the result. So this is our time-independent Schrödinger equation, or this is our Hamiltonian. So we write it out and we find that we have the energy eigenvalue associated with this ground state wave function is h bar omega over 2. So actually the bound that we saw on the previous board is saturated. And so this is the ground state energy, or the 0 point energy. We found the bottom rung of the ladder. So the ground state energy, or the 0 point energy, we denote it E0. And we can find now all the other energy eigenstates and eigenvalues using our raising operators starting from this lowest rung. Okay, so let's leave it at that for this video. Thank you for your time.